Mario is our LIP director, PI of the SWGO group at LIP, and a full professor at TST. Of course, that Mario has a remarkable scientific career. He did his PhD in nuclear structure functions with his PhD advisors, including Jorge Dias de Deus and José Maria Gago. Since then, Mario has worked in an extensive and rich selection of topics, all devoted to particle physics. So hadron fragmentation, polarization studies, jets, among others. Some of them were naturally done within several collaborations, such as NEA 38 and Delphi. In the more recent years, Mario moved from collider to astroparticle physics and was, during several years, PI of the Pierre Roger group at LIP, with an intensive activity in hadronic physics and development of new detector concepts. More recently, Mario works towards the creation of a new collaboration called the Southern Wide Field Gamma Ray Observatory, kind of extensive name, which will be today's topic. So Mario, thank you very much again for accepting our invitation. And please, if you can share your slides.
You seeing it?
Yes.
Okay.
Yeah, exactly.
Okay, so thank you for this opportunity to give a seminar. And Liliana, thank you for your words, but just a small note that remind me that I'm quite old, or perhaps too old. And so don't take my seminar as an old guy. Take it as someone that wants to be judged by his, in every moment by his scientific work. Of course, it's different that it was 40 years ago, but still should be judged in terms of science, not as director or whatever. That's not the moment for that. Okay, but anyhow, thank you for kind words. So, what is the subject of this?
É uma transportadora, não é?
Sorry? It's okay? Are you listening?
Yeah, we are listening. Thanks.
Okay, so what is the subject of the seminar? So I'm trying to convince you that there is a nice opportunity to work on the building of a new window to the universe, basically on gamma rays, building a new observatory in South America. And of course, what I'm going to say, it's my own words. So it's not any official statement of whatever for the collaboration. And most of what I'll say it's consensual, some are not. So, and we'll see in the future. So, but let's start with physics. And physics, okay, you look what's the sky, and you know these pictures since long time. I'm sure always this when in the last 20 years. This is the spectrum of the cosmic rays, charged cosmic rays. It's quite interesting, going from many orders of magnitude, and both in flux and in energy. So everybody knows that at low energies we have a lot of particles. This is the chambers, neon chambers that we are producing at LIP. Very nice, 1 particle per square meter per second here. And at extreme energies, that is one of also my favorite terms, is OG, at 10 to 20 or something like that. I'm not showing that because the seminar will be not on charged cosmic rays, it will be on gamma rays, but we should be present that these charged gamma rays are there, and they are the most important background that we have to fight for. Of course, we will also analyze data on charged cosmic rays, but the main worry is to fight against this, because what we want to observe is the photons, is the gamma rays spectrum. Here you see as a function, okay, here for some reasons, so wavelengths, and here you have the energy. So at very low energies, we have the cosmic microwave background. You see nice peak, thermal peak. What we are talking and discussing here is the region between GV and PV. That's what we are discussing here. And here, this is a plot that has already a few years. And if you look in this region, we have basically arrows. That means that are limits. So in that time, there was just a few observations in all these regions above the many hundreds of GV, TV, and so on. Here, I just plot what is the spectrum of cosmic rays, and you see clearly that it's well above, and in this region is a factor of 10 to the 4. That's why it's should not try to, you have to reject this charged cosmic rays. Okay, that's the general picture. So what I'm saying is this region of the what is called usually high energy and very high energy gamma ray sky, that we are talking about MEV, GV, TV, and so on. 20 years ago on TV, there was 0. On hundreds of MEV, a few, and this has changed a lot in the last 10, 20 years. Now, this is sky coming from one of the satellites I showed, satellite, this Fermi. Above 100 MeV, you have more than 5,000 sources identified, positions. And even if you go to above 100 GeV, the number of sources is quite impressive. It's increasing every year. We have already more than 200. Of course, here you have a lot of sources. This is the galactic, in the galactic plane, that this is this line, and here you have the center of galaxy that is quite populated. So for sure, there is no more the question if there are something to observe. There are a lot of things to observe. So what is new? What is important to observe? What is exciting? Why we are so excited to add new sources, whatever, what you have to want to study. So one of the things that is important as the sky is not static. So here is we are changing the day, is a kind of photos of several days, and you see that we have sources that get very intense and change, appears, disappears. So it's not a static picture, and that's very nice because I don't like things too much static, and really it can be very fast. So if you want to see things that you have well-known, sources that are well-known and can be followed, and you see that the intensity can change very, very fast in orders of the minute scale. And so you have flares, and whenever you have flares, you have something interesting to observe it, to understand what is the physics behind. And people from the of physics will be very happy and are very happy whenever we can study in detail structure and of the flares. But you have also things that appears and disappears in skies. One of the most famous is the gamma ray burst, and gamma ray burst was the mystery for many times. Now you have the duration time, and clearly you see that we have two populations. We have short gamma ray burst that typically goes off the second scale or below the second scale, and you have long gamma ray burst that goes until hundreds of seconds, 1,000 of seconds. But anyhow, it's a fast process. Light appears and disappears in sky, and that's the most intense objects in sky with enormous quantity of energy. Nowadays, I'm not going on to physics, so nowadays you know that the long gamma rays is the collapse of a big star. The short gamma rays is the merger, creating a black hole and things like that. Anyhow, the gamma ray bursts are also very important to go on to past, because if you see the population of gamma ray bursts that has been observed, we have even one that has a Z equal 8. That means that were formed in the beginning of the universe. And it is quite remarkable. Of course, if you go very far in the past, your energy thresholds are decreasing, but okay, but that's very important. And so we have sources, point sources. We have sources that change very fast, but we have also extended sources. I would perhaps you know already, but that was one of the big discoveries in the past few years in this kind of chapter, is to understand that from our galaxy there is this kind of emission from big bubbles, and that remind us that in our black hole that are in our galaxy, once upon a time, perhaps it was active, and you have some remnants of such of jets from even our own galaxy. And that was very curious, and it's also very important. And of course, this is nowadays well studied, except on the very high energy, and you have several models, important models to explain the mechanism that are behind this, and these are critical on the high energy. And here again, you see you have just limits. Of course, I could talk about that method, but there we have no positive results. You have limits, but anyhow, that method will be always extended regions, and you need a wide field observatory, and we'll go to that in a few minutes. In the last years, the field was very exciting, because you have several channels. We have the cosmic rays, the gamma rays. You can have like, for instance, IMS. Everybody knows IMS, observing the nuclei. We have neutrinos. We have a lot of people on neutrinos, solar neutrinos, astrophysics neutrinos, and things like that. That has been studying and developing along in the last years of the last century, and very active in the last 20 years. But what was really new was the simultaneous observation of flares, of bursts in more than one channel. In more than one channel, you could have gravitational waves. Also, gravitational waves is a very important channel, a new channel. And now we are in what people usually call the multi-messenger era. So if you want to understand really the source, you should observe it in all possible ways. And all possible ways means photons, neutrinos, gravitational waves. Okay. Then that's okay. We knew already that was in 2017, that was the first multi-messenger event observed. And what is very new, perhaps not nobody knows, it's from this year, May this year, is that now in gamma rays, that the Chinese collaboration LASSO in the Himalayas has observed for the first time PV photons, sources that emit photons at PV, and they have reported in their first publications 12 sources discovered. And this is a kind of revolution, because we know that we have in our galaxy photon sources, and if you remember, 20 years ago we were talking about TV sources, trying to go to TV sources. So that's very important. So all this field is very active, is moving a lot, and in its, of course, observatories and to look for the sky. One way, the best way to catch gamma rays is to go above the atmosphere. And then you do your favorite particle physics detectors, calorimeters, tracking, whatever. You put them on a satellite, you just try to catch them. That's very nice. The problem is that satellites are small, and this is the best one that has made most of these sky maps from this Fermi satellite. The problem with this Fermi satellite is 1.6 by 1.6 square meters. So is less than 4 square meters, 4 square meters. This is good if you have a good flux. So for low energy, that means until GV, above the GV range, 10 GV, something like that, it's too small. So you cannot put, and it's too expensive to increase in by another magnitude, whatever, the size of the satellite. Okay, one day you can build something on Moon, but we are not still there, and then you could catch directly gamma rays, and then perhaps you can have a bigger surface. So we have to go to ground, and for that we have to use the atmosphere as part of our detector. And what happens in the atmosphere is that you know already, you have interactions on top of the atmosphere, and then we have a shower, and you develop the showers, and then you catch some signals from these showers. You can catch, I go back to that, the light produced by the development of the showers, or you can get both the particles that arrive at us in this shower. Okay, so to remind you that we have photons and protons and ions, and these showers have difference, hopefully, because we want to distinguish. And basically, the main difference is that the photon is basically electromagnetic, sometimes electrons and photons. Sometimes you can produce muons, of course, but there are very few muons produced by electromagnetic shower. And in the hadronic shower, you have a skeleton, a core of hadronic reactions, and then of course you have pi zeros, and then you have photons, and then you created several electromagnetic showers. So we have a much more complex picture from this side, and we have pi zeros, but we have charged pions, and charged pions produce decay and produce muons, of course, neutrinos and neutrinos, but you don't catch them. So muons are an important signal of hadronic showers. To get an idea how it looks like, these are of course simulations. This is the shower, so this is the longitudinal profile of the shower. This is a cut of the shower at some mean point, and you see what looks like electromagnetic showers. So we have something that is well dense near the core region, near the axis of the shower. This is 50 GeV. That's what you want, the lowest energies that you would like to catch. This is 1 TeV. So it's okay, it's fatter, but still same picture, very dense near the axis. If you look for 100 GeV proton, you see that is quite different. You have many subclusters, and you have a structure that is quite different from the gamma. The problem is that this is simulation, and what you observe is not with these details. So what you observe, as you see, is just a convolution, the particles that arrive at us, the light produced. So it's not so easy as it could seem to separate the two things if you want a rejection of the protons of the others 10⁻³ 10⁻⁴ 10⁻⁵. So to separate 1 on 10, it's easy. 1 in 100 is still easy. 1 on 1,000, okay, but then you start to be difficult because there are tides, fluctuations of showers. You can produce a pi zero in the beginning with a lot of energy, and then all this picture will be a tail, and that's the real problem. Okay, so how you detect the showers? So I was saying that you have the particle entering the atmosphere. The particle entering the atmosphere, you develop the shower, and then you have you have Cherenkov light in the atmosphere. You have also fluorescence light, but that is the technique for charged cosmic rays like OG. Here we are looking for the Cherenkov, the cone of Cherenkov light produced by the relativistic electrons in the shower, and this cone is quite narrow. It's 1.7 or 1.3 degrees. It depends on density of the air, but okay, it's quite narrow. And then, so if you are lucky that on the bottom of this pattern on the ground, you have some telescope looking for this Cherenkov light, then it's very nice, because then you can reproduce well the intensity of the signal, some shape, somehow the shape of the shower, the core, and things like that, direction and things like that. This is very powerful, but a telescope goes looking a narrow open field. The other technique is the old technique of cosmic rays detectors. It's just to put detectors on the ground and try to catch the particles that arrive at the ground. What we are going to talk is the detectors like in OG. It's basically water Cherenkov tanks, so it's tanks of water. And what you get is the charged particle, relativistic charged particle entering in the water, gives a Cherenkov light now in the water, and you try to catch this light by some photon multipliers or whatever you want to put, silicons, whatever, and the photons will convert and give the shower, electromagnetic shower, and you have the signal. So these basically the two techniques that we are going to discuss. Of course, you can put also scintillators and RPCs and things like that, but I'm not going to stress this in this seminar. So an example of the Cherenkov telescope magic, it's very nice. It's in La Palma. I hope that the volcano will be quiet soon, and people go to normality also, and they have very nice results. And for an example of the ground arrays, we have LASSO in the Himalayas, Chinese, that is the bigger gamma ray observatory existing nowadays, and it covers, or you covered, it's almost ready, 1 square kilometers. This area is 1 square kilometers, and you have here a central detector with more detail or whatever, and this is ponds of water, whatever. You go back. So that's the type of detectors we are talking about to detect the showers. So these are called ERCTs, Imaging Atmospheric Cherenkov Telescope. They have narrow field of view, but a very good energy and angular resolution. These ones have a very wide field of view, are observing all the sky, always, but have a poor, okay, poor, that means 10, 20%, 30% that we can discuss, and you have much poor angular resolution, but you have about 0.1 degree, 0.2, 0.3 degrees, more or less in these orders of magnitude. So, but it's clear it's poor in angular resolution and energy. So this kind of observatory are complementary. So what exists in the world nowadays? Nowadays, that's the image of the world. So in red, we have this telescope. In blue, we have these ground arrays. So in telescope, we have in Namibia, we have HESS, you have Veritas, and you have MAGIC, and they will build CTA, okay, both in Canarias and in Chile. If you look just for ground arrays, nowadays operating, we have basically two observatories. This LASSO, this big one, with covering an outer array 1 square kilometer, and you have the WOC one that is basically American, Mexican, German collaboration, but basically American, Mexican collaboration that, if you want, is covering just this central part of LASSO. And if you look on that, there is nothing on the south hemisphere, there is nothing. And that means what? That means you just observe half of the sky, under the sky. You don't observe the southern sky. And in the southern sky, you have also our center of our galaxy. That is one region to study sources in galaxy, that nearby sources, the dark matter, whatever, is the most important region. So it's clear, one of these days, someone should build an observatory on the south hemisphere. And if you look on the south, the best region to have to go up in altitude to decrease the energy threshold are the Andes. And I like the Andes because I've been in Uruguay since 15 years, and I like the Pampa and South America. So we intended to go on this direction and to extrapolate what we have learned also in Uruguay to this new kind of field. So the idea is to build somewhere in South America this new observatory at high altitude. So this was an idea that starts already 5 years ago or something like that. Of course, people wanted to replicate it, to do a walk south. We wanted to do much better. At some point, there was a lot of tensions between the groups. We were the newcomers and people that are there didn't like too much newcomers, as always. They want people to help them, but they know everything to do. But at some point, we were able to put together in a meeting in Lisbon in 2019, in May 2019. We converged, and we have found a new, I will call collaboration. Start with the R&D project, but clearly now it's a collaboration, and it's increasing collaboration that now has 53 institutes from 13 countries, and we have already about 100 whatever researchers. Of course, there's always this question: who are there just to give political support, whatever, or are working? But now we have already a community of many tens of people really working there, and it's very nice. And we are in design phase, 2019 to 2023, so we are really in the middle of the design phase, which is a very interesting phase, because you have crazy ideas, you are allowed to propose things and to follow crazy ideas and new things, and we are doing that very intensely at Lisbon. And not only, but also. So this observatory, you have this the sky map. So here you have the center of the galaxy, and here you have the region that SWGO will cover in the sky. In blue, you have the region of fog. You have some superposition area that is good, but all this region is just observable for SWGO. So you have all this sky, south sky, to observe. What is science? I have talked a little in the introduction. You can have science that you can plot in terms of the time scale. So you have things that are very fast, seconds, as a gamma ray burst, as I was talking. And these are things that may happen very far away, so more than 1 gigaparsec. We have active galaxies. I have shown you the flares. We have extragalactic, and then nearby you have galactic of the galaxy physics, and of course we have observation of dark matter and things like that. And then we are talking about extending observations during many long periods, years, scales, and things like that. So it's very diverse on time scale and on distance, on source that you can and should observe. So in terms of energy range, what we would like, that's our dream, at least at Lisbon and for part of collaboration, is to cover all this big wall. What is this big wall? It's between satellites. So we have again Fermi that goes until tens of GeV, until the Pierre Roger, and that goes until okay, now with low energy extension 10 to 17, 5, 10 to 16, something like that. So that's what, and physics, that's what I was talking about. And also this is cosmic rays. This is the map of cosmic rays. That is also very nice feature to exploit. Okay, that's what you would like to do. It's very ambitious. This in the last 1 year, we have our science group in SWGO have translated all this physics in performance targets that should be used to benchmarking the detectors proposal that are being building and sites and things like that. And in Lisbon, we have been particularly active in this area of transients. We start our life there, and now we are starting to be very active, or starting to be active on this PV area. So we basically would like to cover the two extremes. So then the question is how big you should build. Of course, the good answer is as much as you can afford. But what is the scale? Scale is statistics. So if you go to 10 TeV, and if you build something covering 100,000 square meters, then you could observe 1 million events per year. This is quite comfortable. So if you do the 10 TeV region, you can build something of this order of magnitude. But if you want to go to PV and to have some statistics to observe and to accumulate and to study, and that means between 10 and 100 events per year, you have to be on square kilometer region. So that's basically the regions that we are discussing. OC is here, so is 20,000 square meters. So that means okay, you have 5 times less events than here, but okay, very nice physics. And in terms of radius, to have an idea, this is not OC, sorry, OC is 20,000. You should have a radius of 160 meters. This is the compact array, and last a radius of 560 meters. Then, of course, you have to cover an area, and you have to put detectors. And then you have always 2 options. You can put detectors very nearby, so to have a very dense array, or you can put detectors more far away. So that's what you call the fill factor. Of course, if you have money, infinite money, you will cover all the surface with very compact. But okay, with limited resources, we have to choose the density that is enough to do whatever you do. So if you try to understand what you would need as fill factor density on these PV regions, where really you have to cover a very big area, you have okay, that's kind of simulations on the number of stations that will be needed, and as a function of the events that you want to observe, and you understand with this fill factor 0.25%, that's not too much, you can still have you can do the job with a reasonable number of stations. You don't need an infinite number of stations. So this is what would look like an observatory with a field factor of 0.25 in covering 1 square kilometers. Then the other question is where. So I have told you already that should be in South America, because that's the region where we can have go to 4,000, 5,000, even 5,000, between 4,000 and 5,000. We have many possible sites. Now we have identified 8 possible sites where local people are proposing as possible sites of observatory, and you are entering in the 22 will be a crucial year for SWGO, because you have to choose site, and you have to choose what to put on site, 22, 23. And you go to reduce and try to have conditions and things like that. But basically, we have a very good site near Palma in Chile. We have a good site in Argentina. We have also several proposals of sites in Peru and also in Bolivia, but Bolivia perhaps is more complicated because it's not so large. So flat and large. We need some surface that is reasonably flat. Okay, but that's will go. And then, of course, the question is what kind of detectors we want to put there. So, looking in what exists nowadays. So we have the experience of OC. They are the water tanks, but they are big water tanks. So you see, so we have some hundreds of water tanks like that. And near Glasso, we have these buildings, and inside these buildings you have swimming pools, so ponds. And outside the swimming pools, we have some scintillators, but we have in these mountains behind the earth, you have also water Cherenkov tanks in concrete to catch muons and to filter the electromagnetic contamination. So that's Lasso. So in Lisbon, you don't like these kind of things because they're too big, so you see what we are proposing. So in collaboration, what are the proposals? One is building it with water Cherenkov tanks, that was I referring. The other is to find a good lake. There are not a lot of lakes like that, but there are 1 of 2 possibilities or 3 possibilities, basically in Peru. That there are problems, but there are people that want to do it. And then you just put your detectors floating in the water, or you are building the pond with these swimming pools, people that are proposing it in SWGO, they don't build the roof. I don't know if it is a good idea, but that's another kind of thing. If you go to our favorite option of water Cherenkov tanks, here you see that there are a lot of difference. We have these big tanks like OC, or you can have smaller tanks. So what we are proposing is to going to small tanks. Small, basically the orders of magnitude of Auger, perhaps a little bigger than the tanks of Auger. You have still to discuss. And what we are discussing is small tanks with 1.5 meters of water or something like that. The others have 4.5 meters of water. They have much more waters. So the difference in quantity of water is quite big. And for the moment, for reference, we have a diameter of 4 meters, but perhaps we will reduce it. And in our proposal, we are proposing 4 PMTs to look for the symmetries. Now we are working in a design with 3 PMTs and not 4. And I hope that give good results, and they can go to this design of 3 that have several advantages and is less expensive, because PMTs are expensive. That's another thing. So with this idea of small tanks, the idea was and is to explore the symmetries between single muons and electromagnetic events. The idea is that a single muon, so you have a single Muons gives basically signal in one of the photon multipliers, on two of the 4 photon multipliers, and so you see clearly that is the trace in each photon multiplier, and you see clear that you have a PMT with a lot of signal and almost no signal in the others. If you see for the if you see an electromagnetic event, most of them will be much more symmetric because we have a shower that is developing inside the water and not just a trace going inside. So that's one of the things that you are doing, were doing in the last year, and you get very nice results using machine learning techniques, and we were even able to calibrate the Muons with this kind of things. And that's one of the big questions: how good you can identify Muons without filtering out the electromagnetic contamination. And one of the things that we were, of course, discussing and trying to understand is what would be the energy resolution that you could achieve. Then we have also make a lot of progress here in Lisbon, because what LASSO has nowadays for the vertical showers, what they quote is something above 30% of resolution at 10 TeV. So this is star, and we think on simulation that you can achieve a factor going to 20%. If that is true, if you can convince people that this is true, at least the article was published, that's a good thing. Then, of course, you gain a lot on the energy resolution, and if you gain a lot on energy resolution, you gain also a lot on background rejection, because you integrate much less background. And of course, that is a dream, that is the intrinsic resolution that you could achieve with this method that comes from the intrinsic shower fluctuations, and not if you have an ideal detector, could perhaps achieve something like that. But okay, you are there on this sick headline. So how to build this? Our proposal was to build this observatory by phases. So having a phase starting with a very compact array covering the size of OC nowadays, then build the LASSO area, then increasing the compact array, and then at the end increasing even the extended array covering up to 5 square kilometers. That was our layout proposal by stage, by phases, and the good thing is that at each phase there are clear scientific goals that can be associated, and so the idea is to build, our idea, not all people in collaboration, is to build something that will go for 20 years, 30 years, like OG, and then you are you are building along the money that you can get from funding agencies, but also boosted by the physics results that you are achieving in UI, because of course, if you have very nice, interesting results with the first 2 phases, it will be much easier to convince the agencies to go a step further. And this kind of exercise, which detector we have to do, what is the extension, how we cover the area, what are the priorities in terms of physics, what the money in terms of the money that you can get in principle, what you should build, that will be all the positive and negative discussions that we have during 22 and beginning 23. So it's very exciting times and we are very motivated, but okay, let's see what happens. So, okay, that's this technique. So you can have a variable number of PMTs, 4 PMTs in our option, perhaps just 1 or perhaps 3. Okay, that is in progress. And what is the ambitions in terms of sensitivity? In terms of sensitivity, so you see the energy range, you have the sensitivity in terms of flux. This is the present OC. This is the present, okay, is LASSO. LASSO is working already in the high energy, is not yet publishing results in this part, but is the expected sensitivity. For OC is already working since many years, so it's the real one. So this is kind of simulation here, kind of head of observation. For comparing, I was not referring to CTA, but that's the future project of imaging sharing of telescopes to have, if they are ever built with the density of telescopes they are proposing, because the scale of money is quite high. So let's see if they can get the money for that. And you see that nobody can compare in sensitivity to them below some tens of TeV. That's not true on the highest energy because they are limited by the size. So clearly the highest energy is for ground observatory. And here sensitivity CTA, but the transients, everything that is fast has to be observed first in this wide field, and then you can give alerts for something that goes for of scale of more than 10-20 seconds. That's the time of pointing for these EICTs. For gamma ray burst, short gamma ray burst, the point is too short to give to observe something interesting. What we would like to do better, as good as possible. So to do better is to go below the present energy threshold. OC is basically of the order of 500 GVs. They quote 300 GV, but they are not there yet. So several hundreds of GV, that's the energy threshold. Clearly, we would like to go below 100 GV, if possible, until 50 GV, and going up in this high region. When I have shown this 6 months ago, people thought that I was completely crazy. That happens sometimes. But just for curiosity, the official plot nowadays of LASSO, of SWGO, is not so different from what I was proposing and replicating. So if you see this is what they call the low energy enhancement. This is what they call the high energy enhancement. And of course, if you have just a lake, you are just observing this mid region and you lose all the exciting physics on low energy and all the exciting physics on high energy. But now they have understood that perhaps we should consider seriously this. Going back, I'm finishing. So that's for doing that. Of course, we have to worry about energy resolution. We have to worry about angular resolution that I have not discussed, and we have to worry about gamma discrimination that will be the key factor at very high energies. And of course, you have to worry about effective area and how you to cover and how you to fill your detector. And that's the game where we are, deep in the game. The group is quite active, it's increasing. We have 2 new PhD students, one from Spain, from Córdoba, that I think is listening, and a new one from Torino that is arriving, and we have some master students from Portugal, and I hope that we have PhD students from Portugal in a short term also. So that's our challenge and also our responsibility in the sense that we should try always to do the best with the possible money and the human resource that you have, and you have to mobilize them to have fun, but also to do good science. Okay, thank you.
Thank you very much, Mário, for this very insightful seminar.